Hello, USHS students. In our last lesson, we looked at observations and inferences, trying to identify what the differences between those two would be. What we're going to do today is we're going to dive a little deeper into the scientific method, and we'll see where those observations and those inferences come into play. So, during this lesson, you need to keep in mind that you need at the end to be able to identify what the different steps of the scientific method is. You need to be able to describe the important components of the scientific method. So what are all those different variables? What are the different steps? What do you have to go through first, second, third? And of course, you need to know what your vocabulary terms are. Again, it is advised that you keep track of all of these vocabulary words, whether it be in a Word document on your computer or in your notebook. So, for the scientific method, our first essential question is, how do we conduct a scientific investigation? Now, what we're going to start with first is a little video that goes over, and it has some nice cartoon images of what the scientific method is and a little bit of history of it. So we'll begin with that now, and then we'll complete their notes right after that.
Why are some kids sad? What makes the wind blow? How do birds fly? Our world is full of curious phenomena. To find answers or solve problems, we can use a process which was first acknowledged by the scientist and philosopher Ibn al-Haytham in the 11th century. Also known as Alhazen, he is considered to be the father of optics and the scientific method. There are 6 steps to it. 1. Observe and ask questions. 2. Research. 3. Formulate a hypothesis. 4. Test your hypothesis. 5. Conclude. 6. Share results. The goal of the scientific method is to find out the truth. Let's try. Step 1. Observe and question. Observation helps us formulate challenging questions that you will be able to test. A good question converts the natural sense of wonder into a focused line of investigation. When is the best time to drive to school? Which food is my dog's favorite? For example, if you observe that women smile more often than men, you might ask, why do women smile more often? Step 2. Research. Find out if other people have asked the same or similar questions. If you research online, use search terms like study, research, or meta-analysis, which is a summary of research for a specific topic. Read as much as you can about your particular subject to see what you can find out about. For example, research happiness based on gender or study the science of smiling in different cultural contexts. Step 3. Formulate a hypothesis. A hypothesis is a theory that you can test to see if your prediction is right or wrong. From your observation, you have noticed that women smile more often and that people who are smiling seem to be happy. From your research, you know that there are different types of smiles: shy, genuine, and false. In one paper, you read that baby girls smile more often than baby boys. Here is a hypothesis. Women smile more than men because they are happier than men. Step 4. Test your hypothesis. When you test your hypothesis, you want to make sure to do this in a fair way and that the conditions are constant. For this hypothesis, we can design a test where an interviewer talks with a set of men and women for 5 minutes each, counts how many times they smile, and then asks each one to rate their level of happiness. To get a good sample of the population, we invite 300 women and 300 men. Seems like a good test, right? But wait, what if the interviewer is a woman and men tend to smile more at women? Or vice versa? Or what if the topic discussed is one that interests women more than men? And what if people aren't reliable reporters of their actual level of happiness? So clearly, we would need to be much more careful. Step 5. Analyze and conclude. Let's assume that you designed a very careful experiment, controlling for as many variables as possible. Now you can analyze the data to see if your hypothesis is correct or incorrect. Depending on your findings, you may want to change your hypothesis or change the design of your testing. Perhaps you have discovered an even more interesting question. This stage of the scientific method can be repeated as many times as necessary until you find just the right hypothesis and test method to find accurate results. Step 6. Share the results. When you are satisfied that you have proven or disproven something important, report your results. In science, it is important to detail your methods so that your peers can review your work, which is a critical step to getting published. If your results are solid, your experiment can be repeated by other scientists. Such reproducibility is a sign of good scientific work. But failed results can also be interesting. An incorrect prediction could prove to be important and should always be reported. To make sure you get it completely right, here are 3 more things you can check before you publish. A. Any scientific theory is falsifiable. Real scientists know that there is no such thing as a scientific proof. In other words, you can never prove your theory to be 100% right. All you can do is find a lot of supporting evidence that it could be correct. Here is one example. Say that someone says, hamsters can fly. We cannot prove that this is false. Yes, we have never seen a hamster fly, but we can't test all possible conditions or look in all possible places on the planet to know that all hamsters never fly. Maybe a space hamster does. So while we can often prove that a phenomenon exists, it's much harder to prove the non-existence of something. If your theory can't possibly be proven wrong, then it's not falsifiable and hence not scientific. B. Correlation is not causation. When you analyze your results, it is important to separate between 2 possible reasons: correlation or causation. Let's say you hear that towns that have more churches also have more bars. Could it be that religion makes people want to drink, or that drinking helps people to find God? If you add more facts, such as larger towns have both more bars and more churches, you can see that a larger population is a more likely cause of higher numbers of bars and churches. There is probably a correlation, but no causation. If we compare men with women and would conclude that women smile more and are more happy, then this still doesn't mean that it's happiness that makes them smile. Maybe they just eat more chocolate and cookies, which makes them both happy and smile a lot. C. Avoid selective windowing. When you publish, you've got to show all relevant facts. Colgate once ran an advertising campaign claiming that 80% of dentists recommend Colgate. What they didn't tell us is that when they asked dentists to select their preferred toothpaste, Colgate was just one of many other brands they also recommended. Colgate was later sued and forced to take down their misleading ads. The purpose of science is always to find out the truth and nothing but the truth. To use science to mislead us is wrong and terrible business practice. Let's do a last example together. I have 2 coins. One is bigger. Why? The small coin says 1 cent, the bigger one says 5. Aha! Small coins are worth less money. Bigger coins are worth more money. I pull some more coins from my pocket. 2 more pennies, 1 more nickel, and $0.25, which is 25 cents. Great, my hypothesis seems true. But wait, is the quarter worth more because it is bigger? So is that a correlation or a causation? My sample size is pretty small. I don't think I am ready to report my results. Can you help out? Please apply the scientific method to study your local currency. Maybe you have a hypothesis that we can test until we get solid, repeatable results to report. Please publish your findings in the comments below.
So hopefully that was a little bit of a review and maybe a few new pieces of information that you may not have known about before. All right, so what exactly is science? Science is the systematic body of knowledge that includes you making observations. There's that term that we went over in the last time. Okay, using those five senses, formulating an inquiry or question. You've got some observation, you've seen something, smelled something, tasted something, and you're wondering what in the world is going on with that. Okay, you're forming a hypothesis, that educated guess. Now, a lot of times, whenever you're looking at the scientific method, there's one small step in between those 2 points, your observation and forming that inquiry to forming a hypothesis. There's a very important step that's often overlooked, and we're going to hit on that. All right. After you form your hypothesis, that educated guess, now see that educated guess, it really does, one of the big key things with that is that it has to be testable. All right. You got to be able to perform an experiment in order to prove or disprove what that hypothesis is. We go on to our next step of the scientific method, and that is analyzing the data. So if you're trying to figure out what did I actually discover in my experiments, that's where the analyzing comes from. All right, what errors did I make? And then lastly, you have a conclusion that you're going to get from that information. And after you've made that conclusion, you'll just share that information out to other scientists, so that way they can maybe try to reproduce your results, try to improve on what you're doing, or maybe further your investigations. So, first step, and no one can disagree with this, our first step in any scientific investigation is simply making an observation. You're becoming aware of some object or some event that is out there, and you're gathering information with your five senses. And what you're trying to do is you're trying to figure out what information do we need to gain to further an investigation. What are we trying to come up with? All right. Are we trying to discover a cure to something? Are we trying to make something easier? I'm curious at why the lily pads seem to be exploding during this time of year in the pond. All right. So in order to drive the scientific method, you have to make some observation and you have to start questioning it. All right. This is a step that I said people oftentimes just bypass. All right. Because a lot of times, whenever we're trying to do simple investigations, and I'm not talking about, something in a science lab. It could be as simple as you're going into a grocery store and you're trying to find where the cantaloupe is. Well, you know from prior knowledge that a cantaloupe is something that you're going to eat, so you're going to find that in the grocery portion of it. So your background research involves your prior knowledge of you going into those restaurants, or not to the restaurants. Well, maybe it'd be at a restaurant. You go to the salad bar to get that. But it would be going into those grocery stores, and you're taking that prior information and you're deducing where that might be. Okay. Now, whenever you're doing this research, sometimes you are going to have to write down your information, because if you're going to try to share that with somebody else, you can't say, well, I saw it on the internet. That's not credible. You have to be able to explain where you got it, cite where it is, so that way somebody else can go to it and see where it was. Is that source credible? All right. Now, the more that you know about your subject, the more research that you do, the easier it's going to be to actually investigate what you're looking into. The more knowledgeable you're going to be. Maybe somebody else has already started some research or done some testing on your subject matter. All right. I know that in sports, a lot of times people want you to take supplements. Well, what research is out there on those supplements? Okay, you are not the first person to ever maybe want to try to bulk up. And if you tried to start from scratch, well, you're asking a lot of yourself. Whereas if you do some research, you find what other people have done, what other results have been, what some hazards might be, then you're more informed. Okay. After you have that research done, you've made your observations, you can start to come up with some sort of question. All right. What question or curiosities do you have? Why are you thinking about this? What is the inquiry you have on that observation that you made? Okay. So, a very famous person or people. Okay, a little bit of history now. If we're looking at Galileo Galilei, according to Albert Einstein, all knowledge of reality starts from experience and ends with it. Kind of makes sense, right? So we have propositions arrived at by purely logical means are completely empty regardless of reality. Because Galileo saw this, and particularly because he drummed it into the scientific world, he's oftentimes referred to as the father of modern physics. Okay, so if we're looking at a lot of the work that these early scientists had done, they really put a lot of thought, they put a lot of ingenuity into figuring out ways to solve the problems of their observations. Why did the apple fall from the tree? All right, we're staging those observations and we're watching what happens and occurs, and then we can develop some mathematical laws from that. Okay, or if we're looking at Galileo, a lot of information has been brought to us on the motion of objects on the earth. Okay, so thinking and observing. Once you've made that research, now you're able to start to make an educated guess. Now see, here the key is that you have an educated guess. If you blindly go in, if you just have an observation, then you jump right into a hypothesis, you're not doing it right. Okay? You just aren't. You have to have some background knowledge of something in order to properly set something up. Okay? So the most important thing that you need to understand about a hypothesis is that it needs to be testable. All right? So our educated guess has to be tested. Now, there are three ways that we can make sure that we write our hypothesis correctly. First, if we write it as an if-then statement. If I reduce my TV watching hours by 2 hours a day, then my science grade will increase by 15%. See, by us saying very specifically, if I cut out 2 hours of TV watching a day, that's something that I can measure, that I'm going to increase my science grade by 15%. Again, something that I can measure. So that if-then statement is very directed. I have some numbers in there. It is something that I can test. The second way, it can be specified in a null form or null hypothesis, where in the hypothesis is stated in the negative form. The third way it can be asserted in operational form or an alternative hypothesis. Now we're going to watch a quick little video on the differences between a null form and an operational form right now.
Hi friends, welcome to biologyexamstory.com. Today the topic of our discussion is the difference between null and alternative hypothesis with a simple example. First of all, starting with the summary of scientific method. A scientific method starts with an observation. Then we will be asking questions why, how, what, like that. To define the problem, the next step is formulate a hypothesis. And this is the point which we are going to discuss in detail. And this is followed by conducting experiment to find out whether the hypothesis is valid or wrong. And then we'll be drawing conclusions, that is accepting or rejecting the hypothesis, and finally publishing the result. First of all, starting with the definition of hypothesis. Hypothesis is an educated guess, a possible answer, or a predictive statement that can be tested scientifically. So it's based on previous experience on the topic, or by review of literature, or based on existing knowledge. In an experiment, there are two types of hypothesis: alternative hypothesis and null hypothesis. So let's explain the concept with a simple example. And this is an experiment. The researcher has defined the problem, effect of biofertilizer X on plant growth. Suppose the researcher has a new formulation and he wants to test the effect of that biofertilizer on plant growth. Alternative hypothesis is a hypothesis that the researcher tries to prove, and it is denoted by H1, and it is simply the opposite of null hypothesis. In this experiment, the researcher is actually applying biofertilizer X, and he is predicting that this biofertilizer X increases plant growth. So therefore the alternative hypothesis for this problem is application of biofertilizer X increases plant growth. Whereas null hypothesis, it is just the opposite of alternative hypothesis, and it is a hypothesis that the researcher tries to disprove or nullify. It is denoted by H0. The null hypothesis for this particular problem will be application of biofertilizer X do not increase plant growth. So alternative hypothesis is the hypothesis that the researcher tries to prove, whereas null hypothesis is the hypothesis that the researcher tries to disprove. Now moving to the second difference. Alternative hypothesis predicts that there is a statistical significance or relationship between the variables in the hypothesis under study. In this experiment there are two variables. First is the independent variable. It is a variable that the researcher changes. In this experiment it is the application of fertilizer X. Whereas a dependent variable is a variable that is affected by the change in the independent variable, or in other words it is dependent on independent variable. So application of fertilizer X may affect plant growth, number of leaves, number of fruits, etc. Therefore alternative hypothesis predicts that there is a relationship between these two. Change in independent variable significantly affects dependent variable, or the researcher predicts that application of fertilizer X increases plant growth, number of leaves, number of fruits, etc. Whereas null hypothesis predicts that there is no relationship between these two variables. Application of biofertilizer X do not increase plant growth. This independent variable, that is application of biofertilizer X, doesn't have any effect on dependent variable like plant growth, number of leaves, number of fruits, etc. Therefore at the end of an experiment we will either accept alternative hypothesis or accept null hypothesis. So accepting null hypothesis doesn't mean that that scientific experiment is a failure. That actually suggests the refinement of alternative hypothesis, modify the alternative hypothesis to get a better answer for the question asked, or to get a better solution for the problem. And that's it. Thank you so much for watching. You are with Biology Exams for You.
So the next part in the scientific method is the fun part. It's performing the experiment. So after you've stated your hypothesis, you've done some background information, you've made your observations, you've designed your experiment, now we're ready to start testing this thing. Most experiments, they are going to have a control group in it. All right, most experiments are controlled experiments. So what exactly is a control? Well, we're going to look at that variable on our next page. This type always has two test groups. All right, so in a controlled experiment, there's always two groups within the testing. The first group is what we would refer to as our experimental group, and then the second one is the control group. The control group is the standard group. It's the one that you're not going to be altering any variables. You're just going to see what happens in general. Okay. Both groups are the same in every aspect, but the experimental group receives some sort of treatment that's not applied to the control group. So if you're looking at trying to see if a certain fertilizer works on a plant, you wouldn't give the fertilizer to both plants to see if the plant would grow well, because maybe the plant would grow okay if it didn't have any fertilizer on it in the first place. All right, so what you need to do is you need to have one plant, that's the experimental group, that gets the fertilizer, and then you have the control group, that's the plant that does not get the fertilizer. That's the right way to do it. All right, so what are these variables I was talking about? Variables are conditions or characteristics that you, the researcher, is able to manipulate, control, or observe. So there are different types of variables. You have the independent variable, the thing that stands out on its own. It's the conditions such as temperature, amount of sample or characteristic that you're going to be manipulating, the fertilizer. All right. In the experimental research for the purpose of determining its relationship to an observed trend. Will that fertilizer cause the plant to grow better? In every experiment, there has to be one independent variable. It's the thing that we're testing. We're trying to see if it is going to affect the outcome. All right. So an easy way to remember the independent variable is it begins with I. I control the independent variable. If I want to see if adding more salt to ice is going to allow it to melt faster, then I control the salt, then I am controlling the independent variable. Now the dependent variable, these are the characteristics that are going to be measured and expected to change as a result of the change made by the independent variable. All right, here you go. Dependent variable. If we added the fertilizer to the plant, fertilizer independent variable, what is the dependent variable? How much did the plant grow? What's the height of the plant? I can measure that. All right. Dependent variable. It's at what temperature does the salt cause the ice to melt? All right. Now, our control variable, the control variable is the thing that's not allowed to vary. That means if I'm trying to find out if salt is going to, lower the melting temperature or raise the melting temperature, or change at what temperature the ice is going to be a liquid or a solid, I have to have something to compare it to, right? Something that's not getting the salt to it. That's the control group, right? Then we have the extraneous variable. These are variables that are other than the independent variable that may have some bearing on the effect of the outcome of our experiment. So these are things that you have to think about that could cause our results to be skewed a little bit. So maybe in the example of our plants, in the growth, the amount of water that we're adding to it, that would obviously have some bearing on the effect of the experiment. So we need to make sure that both the control group and the experimental group gets the same amount of water and the same amount of sunlight. All right, so here we just have a little graphic, and you can see that in this case, we're trying to figure out which liquid is going to help the plant grow the most. All right, so we have what would look like some pop, okay? And then you have some juice, and then you have regular old water here. So what we're looking at is the independent variable, the thing that I am controlling, the IV, I am controlling it. It's the pop, it's the juice, it's the water. Those are the things that I control. All right, so if I'm controlling the thing that's being added, what's the dependent variable? The dependent variable is how much does a plant grow. So if we measure the height of the plants and we find that the water, the control group, was the one that grew the most, and we know that the pop was detrimental to the growth of the plant. Okay. Now, just a couple of ones here for us to think about. Runners are asked to run as far as they can in a certain amount of time. All right. So what are we controlling? Are we controlling how far the runner runs, or are we controlling the amount of time that they're allowed to run? Well, I'm controlling the stopwatch. So the independent variable is the time, and then the distance, how far were they able to go in a set amount of time? That's the dependent variable. All right. Next one. We have rocks are dropped from different heights and time. Is recorded for the rock to fall from each height. So what am I controlling? I am controlling the height at which I drop the rock. So the independent variable is the drop height, And that means the time that it takes to hit the ground is going to be dependent upon what I controlled. I controlled the drop height. The time that it takes to hit the ground will be dependent upon how high I held the rock. We have different amounts of dog food is given to dogs, and they're weighed every week. All right, what am I controlling? I'm controlling the amount of food I give to the dog. I control the dog food. The thing that we're going to measure, the dependent variable, is the dog weight. The dog's weight depends upon how much food I give it. We have 4 planes fly the same distance, and each of their flight times are recorded. All right, so what are we controlling? It says that they are all flying the same distance, so that's the independent variable. And the thing that we're going to record is the flight time that depends upon our distance that we're flying. So maybe they're different engines, or maybe one has a tailwind or a headwind. All right, so after you have done your testing, you've gotten your numbers, what do you have to do? You have to analyze the data. See, no one is perfect, all right? And what you need to do is you need to look at your numbers and you need to see where are some of the errors that could have happened. So you need to analyze it. You need to think about what went right, what went wrong, and you can't just dismiss something that went wrong just because you don't like it. You have to accept it. It's looking at the errors. And after you have done that, you can start to make some conclusions or generalized statements that you've gathered and interpreted from the experiment. Now, that information that you gathered, in order for you to write a good conclusion, it needs to go right back to the hypothesis. We need to throw that hypothesis in there. All right, so it opens new doors for new research and new experiments, but it does not necessarily end the scientific investigation, because when you form your conclusion, maybe somebody else is going to think of a different way to approach it. Maybe somebody's going to think of something different, or maybe you are going to come up with a different way that you would like to test it to see if some of those errors could be reduced. All right, now, when you are finished and you're satisfied with your conclusion, it's referred back to your hypothesis. The last step, communicate your results. You've compiled your lab result. You've made your formal paper. You've submitted to a peer review. Now, whether you accept or reject that hypothesis, that's not really the point of this. All right. See, when you're communicating the results, you're sharing what you've learned. You obviously have learned something, whether it's the right thing or it's the wrong thing. You've come up with something. What you want to do is share that information out with others, because then they might be able to expand on it. They might want to repeat it. They might want to see what they can do to help you out. And with that, that will wrap us up for the day. If you have questions, make sure that you ask for some help. If you are completed and you're satisfied with all of your answers, make sure that you submit your work to Schoology.com. That will do us for today.